Hello, my name is Paul Sherer. I'm Vice President of Technology Development at 3Com Corporation. Today, we're going to talk a bit about multimedia on the Ethernet. I'm going to begin my talk by laying out some background which explains some of the motivation behind multimedia on the Ethernet. I will talk about computing trends, about what multimedia really is, and why Ethernet is interesting. I will then go into some of the requirements for multimedia networks, and in particular an approach for applying multimedia to Ethernet called PACE. Then I will wrap up by talking about the future of multimedia networks and summarize. One of the clearest computing trends over the past 20 years has been an increased emphasis on communication. This is seen in all aspects of how computers have evolved. One aspect of that evolution is clear computer-to-human communications. A tremendous amount of effort has gone into clarifying what the computer is trying to tell the human. This involves simplifying the messages, adding graphics to the messages, now adding multimedia and video clips to the messages. The whole idea is that we want to make it very simple for the average user to understand what the computer is trying to tell them. The next aspect of how communication has evolved with computers is simplifying the human-to-computer communication. The most outstanding evidence of this is the proliferation of graphic user interfaces over the past 10 years. People respond much more readily toward icons and other graphical representations rather than having to read large amounts of print. Again, it's appealing back to the more basic communication capabilities of humans. Another aspect of how computing is evolving along communication trends is the increasing implicit computer-to-computer communication. It is becoming increasingly difficult for users of computers to know whether or not the programs and resources they may be invoking through their computers are local or remote or across some communications mechanism. This is evolving into creating an information universe around each user to give them complete access to all the information they need without having to worry about where that information resides. Lastly, and perhaps most importantly, computers are evolving to assist human-to-human communication. You can see this in how much desktop publishing has evolved to help writers communicate more rapidly, more cost-effectively, and more clearly with other people. Also in how presentations have evolved to make presentations more graphical, more readily understood. Now with multimedia applications such as video conferencing to directly involve human-to-human communications via video conference, via shared desktop, and via shared whiteboard. In talking through these communication trends, I mentioned the word multimedia several times. But what is multimedia, and how is multimedia defined? Multimedia really has become an omnibus term. It has such a broad meaning and it's so ambiguous, it's hard to understand what it is. So I tend to tell people when they ask me what multimedia means, I say multimedia is what you think it is. If you try to define multimedia, you often get some sort of technical definition which has to do with some simultaneous use of multiple communication forms. I prefer to think of multimedia as an attempt to appeal to several of the more fundamental communication mechanisms used by humans. The most basic communication mechanism, perhaps, is observation and imitation. We look at something, we watch something, and then we learn from looking and watching. Then later we may even imitate it. On top of this, fairly early in our lives, we create a layer of spoken language. Spoken language becomes very fundamental to our day-to-day efforts, and basically it becomes how we think. Finally, on top of that comes a written language. Now, even today, a lot of people don't incorporate written language, but the vast majority of people do. So multimedia takes all these mechanisms, observation and imitation, spoken and written language, and merges them together into a single presentation. By appealing to several of these mechanisms simultaneously, it's been found that interest is increased and retention of material covered tends to be greatly enhanced. Increased interest and improved retention means less time but more enjoyable time is spent learning information. In the information age, an age where information becomes rapidly obsolete, this can be a tremendous productivity benefit and a tremendous competitive advantage. One way of breaking up multimedia into manageable sections is to talk about interactive multimedia versus playback multimedia. The simplest way to think of interactive multimedia is a video conference. All the audio and video information must be received in a timely fashion, or effective interaction is not possible. When you're on a video conference, if there are really long delays in communication, then it's very difficult to speak and very difficult to have an effective conversation. So one of the key characteristics about interactive multimedia is it has to be somewhat real time. Because if there are significant delays, then the effectiveness of communication is greatly reduced. Perhaps the simplest way to think about playback multimedia is to think of playing a tape on a VCR. We consider it okay if when you start a tape it takes several seconds to get going. Then we pretty much watch the tape from beginning to end, maybe stop it occasionally, but we won't move around a whole lot from piece to piece on the tape. However, as time goes on and video becomes incorporated into more and more applications, the line between playback and interactive becomes blurred. Video information is often now being incorporated into reference materials, video databases, etc. This means a few seconds of delay, which is okay when we're just playing back a long piece of material, becomes less and less acceptable because now we're replaying many short pieces of video with somewhat the equivalent of looking a word up. When you look a word up in a dictionary, you don't want to have to wait a long time. You want the answer to just pop up instantly. In this way, even playback multimedia will become increasingly real-time in its application. So what are the evolving applications of multimedia? Well, multimedia applications, as computing in general, share a common thrust, and that is communication. Where the information is stored or live, the goal of almost any multimedia application is to communicate information quickly and effectively. The primary short-term workplace applications of multimedia will become collaborative computing, training, and general presentations. Let's look at one sort of multimedia application that's really suitable for network deployment, and that is telelearning. What is telelearning? Telelearning means learning at a distance. What it means in a network deployed sense is that someone can remain at the desk and take a course. It may be a live course via some sort of television broadcast hookup, or it may be a stored course, which includes video material, which is interactive in nature, and where there are question and answer sessions. But the primary advantage of telelearning, and the reason why it will become important in the workplace, is that it allows a higher level of learning to occur, a higher level of education to occur. While people acquire education, they are still at their workplaces, often still at their desk. This happens without having to pay for travel, without having to leave the work area, particularly without being gone for several days. It allows people to incorporate training as a routine part of the day-to-day efforts rather than making a tremendous outside effort to do some training. Video conferencing is probably what most people think of first when they talk about multimedia applications. It is very natural to be deployed on a network. Video conferencing by itself is typically not interesting enough to most people. Lots of people already have experience with video conferencing and video conferencing rooms, etc. But video conferencing becomes more interesting when it's combined with some other application in what becomes sort of a multimedia application amalgam. For example, a shared desktop. Imagine that you are a user who's having a problem on your network. What you do is click on an icon that connects you to your network help desk, and up pops an image of the person at the help desk. This person can talk to you, you can see the person, and the person can show you things. Then, if you still have a problem, the network help desk person can take over your computer and show you what to do in real time, help you solve your problem so that you'll remember how it was solved, and the next time you'll be able to deal with it yourself. That's the sort of application amalgam of putting together video with a shared desktop that I think will become a very important way that multimedia will propagate into the network infrastructure. The focus of this talk is multimedia and Ethernet. Multimedia is very much in the news these days, but why would you talk about Ethernet and multimedia on Ethernet? Well, the first thing to think about is the networking infrastructure. There are actually several network infrastructures, and we'll go through four of the more obvious ones. The first one is the physical infrastructure. The physical infrastructure is in the end systems, the adapters in the end systems, the cable connecting those end systems to some intermediate system, normally a hub, and then additionally a cable connecting those intermediate systems to other ones, such as routers, bridges, and gateways. When you look at that physical infrastructure, just counting nodes, they're in the neighborhood of 50 million end systems on Ethernet today. Another way to look at this is that 1 out of 100 people on the planet has an Ethernet node. And maybe yet another way to think about this is if all the people who have Ethernet got together and formed a country, and maybe they call it Etherland, it would have the same population as France. This means that because there's so many people using Ethernet now, just the amount of physical hardware is huge and represent billions of dollars of investment. This hardware will be reused rather than discarded as long as possible. So therefore, solutions to address this hardware will be very interesting to the millions of people who own it. Another infrastructure is the procurement infrastructure. Simply stated, the procurement infrastructure is just how products get acquired, sales channels, the representatives who sell the products, the people who buy the products, and how they communicate with each other. Because of the large amount of Ethernet out there, how Ethernet moves into organizations for manufacturers is well established, and people understand it very well. This understanding actually points to another infrastructure, and one that we have to be very careful about, the knowledge infrastructure. The dominance of Ethernet means that there is a tremendous number of people in the world who understand Ethernet, who understand how to maintain Ethernet, and who understand how to manage Ethernet. Again, rather than retraining all of these people into a new technology, it is desirable to reuse the existing Ethernet technology to address new application concerns. The last infrastructure we'll touch on is the application infrastructure. With all these 50 million people on Ethernet, they have to be using it for something. So there are large amounts of applications which run on Ethernet. A lot of businesses have made networking a critical part of running their business. Therefore, they must continue to run these applications, finding a way to incrementally incorporate new technologies into this existing application infrastructure without having to cause a whole lot of change and risk, again, would be very interesting to those people who have Ethernet infrastructures. Ethernet in new shipments is increasingly dominant. Now between 80 and 90% of all networks being installed are Ethernet networks. Ethernet will ship tens of millions of nodes this year and will ship tens of millions of nodes next year. Before any other technology can garner any significant amount of install base, Ethernet will number in the hundreds of millions of nodes. This compounds the forestated problem. It means increasingly that it will be very important to reuse Ethernet for new application whenever and wherever it's possible. A reason why Ethernet is so successful and why Ethernet is dominant is that it has extremely good price performance. The price of Ethernet adapters is very low, often under $100 and even under $75. The price of ports on an Ethernet repeater are very low, usually in the same price range or less than adapters. When compared to other options in lots of real-world scenarios, it's been found that Ethernet performs as well or better than other technologies which may have higher stated bandwidth capabilities. But even as the higher bandwidth becomes more important, another aspect of why Ethernet is interesting is that there is an upgrade path for Ethernet. The 802.3 committee of the IEEE, the group that originally standardized Ethernet, has recently approved a new addition to the Ethernet standard called 100 base T. 100 base T provides for Ethernet operations at 100 megabits per second. So now there are a lot of products coming to market which allow operations at either 10 megabits per second or 100 megabits per second. The advantage of this is still the tremendous knowledge base and understanding of Ethernet. The 100 megabit version of Ethernet leverages all of the knowledge of how Ethernet works and how to manage it, and allows that knowledge to be applied against a much higher speed technology, which can handle applications that require very high bandwidth. In the next portion of this talk, I will discuss what the requirements are for multimedia networking. When you start thinking about any area of applying new products and new technology, you need to discuss prospective users and what they perceive to be important. Based on customer feedback on Ethernet, what is important? One of the first comments that comes back, and not too surprisingly, is to leverage the existing infrastructure. In other words, reuse as much as possible. Another concern is available bandwidth. A lot of people have heard that multimedia takes a lot of bandwidth and can be difficult to put on existing networks. Another very great concern is that multimedia traffic and regular data traffic must be able to be mixed on networks. The existing applications are not going to disappear, so there must be an incremental migration capability to allow migration from today's data applications to multimedia applications, allowing both of these applications to exist together. Obviously, there's an assumption about the quality of multimedia involved and the requirements for multimedia quality, which is at least as good as you get via teleconferencing, preferably at least as good as playback of video and CD-ROM drives. And hopefully there will be some amount of additional quality capability as machines or end systems become faster and faster and more capable of higher resolution, higher definition, clearer video, and other forms of multimedia. So one of the first concerns is bandwidth. One of the considerations for multimedia is to provide sufficient bandwidth for whatever is being transferred to be transferred in a timely fashion. One of the things to consider in evaluating this is that an Ethernet network provides a total of 10 megabits per second of bandwidth. So when we look at multimedia, specifically video mixed with audio, current video conferencing applications typically run at 56 to 384 kilobits per second. In other words, at the top end, roughly 30 times less bandwidth than what an Ethernet network could provide. However, when you look at going to a level of quality of playback equivalent roughly to a VHS tape, using current compression, that takes in the range of 1 to 2 megabits per second to be able to maintain. The next step up is broadcast television. Most people know that when they look at a VHS tape, it's not quite as good as what they see from a broadcast television signal. A broadcast television signal quality would take somewhere between 3 and 5 megabits per second. Again, comparing this to the 10 megabits provided by Ethernet, it's obvious that the quality from the current video conferencing through broadcast television can be accommodated by Ethernet. However, the next step on the video horizon is something called high definition television, or HDTV. High definition television, which has only yet been deployed in Japan, is a much higher resolution, much clearer, much crisper image than we see on current generation televisions. At this point, that requires 13 to 20 megabits per second, which is obviously too much for an existing Ethernet network at 10 megabits per second. However, this could be very comfortably accommodated by a 100 megabit per second Ethernet network. When you get into the technical aspects of multimedia and shipping live video on a network, you get into a couple of technical areas called latency and jitter. Let's look at those terms one at a time. What is latency? Well, latency is quite simply the delay from when data is transmitted. In this case, the data could be a piece of a video image to when that data is received. If the delay is too long, then it becomes very difficult to carry on a conversation or have interactive multimedia. It's kind of like being on a slow telephone link where the person you're talking to is greatly delayed and you're having difficulty conversing because the delay is just simply too much. What causes latency? Well, latency is caused typically by all the systems through which data has to pass and by all the means by which the data is communicated. One of the words I mentioned earlier was compression. Compression means that you're taking the video data, because the raw video consumes a huge amount of bandwidth, and rendering it into a much smaller form, which consumes much less bandwidth. In video, that can often be in ratios of 100 to 1 in terms of the end size to the beginning size of the information. That compression takes time and contributes to latency. There's a certain minimum amount of time and hopefully a certain maximum amount of time. Then, as that data leaves the engine that compressed it, it has to somehow fit in a communications medium. That communications medium may impose a certain amount of latency and a minimum amount of time required to access the communications medium. There's actually a propagation delay on that communications medium, and there may be intermediate systems which introduce their own delay. For example, on a network, there may be a bridge or switch where the data has to flow through the device and the device adds its own latency. When the data finally arrives at the destination, then just as there was a compression phase, there has to be a decompression phase to take the data from its compressed form and restore it back to a video image and display it. All of that also contributes to latency. The other primary consideration is jitter. Jitter is a little subtle to understand, but simply defined, jitter is a variability when, in this case, we're talking video, when the video image is available to be displayed. How can that variability come into the system? Well, going back to the compression phase, some forms of compression, assuming it's used, can find things harder or easier to compress. If it's hard to compress, it may take more time. Also, if that data gets to the communications medium, the communications medium may be busy. It may not be busy. If the data has to wait before it gets access to the medium, it's not always a uniform wait. So there may be an uncertain amount of time it has to wait to get access to the medium. At each of the intermediate systems, there may be a certain amount of uncertainty involved in the amount of time it takes to transit that intermediate system. And then again at the end system, when it goes through the decompression phase, there may be certain data which decompresses more rapidly than other data. What does this jitter do to the data? Well, the simplest way to think about this is to think about video. Whatever is displaying the video displays a new image roughly every 30th of a second. If the data is there to display, then the image gets displayed. If the data isn't there, then the image does not get displayed. So how does this relate to jitter? Well, if there's a lot of jitter in the incoming data, then this may cause some frames, some images to get dropped because it hasn't all arrived by the time it's needed for display. This differs from the effects of latency. If every bit of data experienced equal delay, then once the data began arriving, then there would be no issue of the data not arriving when it was needed for display. Since latency and jitter must be kept low, one often hears of bounded latency and jitter. This simply means that it is possible to specify an upper bound on how much latency and jitter is present. Now we'll talk about the PACE approach. What is PACE? The acronym PACE, everything has its own acronym, stands for Priority Access Control Enabled. PACE, as it is currently defined, is applied to Ethernet. So what does PACE do for Ethernet? The first thing it does is provide bounded latency and jitter, which we just got through discussing. Bounded latency and jitter are important considerations for multimedia, particularly interactive multimedia and other real-time applications such as process control. Another aspect of PACE is that in many scenarios, PACE actually improves the utilization of bandwidth on Ethernet. That is, if you rent a segment of Ethernet in a standard Ethernet fashion and compared it to the results of a segment run in a PACE fashion, the amount of bandwidth that's actually available to be effectively used by the applications will often be higher on a PACE segment. One of the trends in Ethernet networking today is a trend away from repeating towards switching. PACE takes advantage of this shift from shared Ethernet to switch Ethernet. Another aspect of PACE, and perhaps most importantly, is that it works with any existing Ethernet or fast Ethernet adapter. It's able to reuse Ethernet cabling, it reuses the drivers for the adapter, it reuses network management for the adapters. In other words, it leverages a lot of the investment that's already in place. One of the things we just mentioned with Ethernet switching. What is Ethernet switching? Well, Ethernet is normally defined over an entire network, which may be composed of many nodes. There's a single 10 megabits of bandwidth shared by all those nodes. In the switching paradigm, there are fewer and fewer nodes for each Ethernet segment. As this shift in paradigm comes to its logical conclusion, you end up with Ethernet workgroup switching. In Ethernet workgroup switching, most of the nodes in the workgroup have their own Ethernet segment. That means they have their own 10 megabits. As we saw earlier in looking at the bandwidth consideration, if an end system has its own 10 megabits, then a lot of the bandwidth concerns associated with multimedia are alleviated. As you can see in this graphic, a repeated work group, when running the Perform 3 benchmark from Novell, gets pretty much a consistent level of performance, regardless of how many nodes are running the benchmark. That is because, with modern systems, 10 megabits can be readily consumed by a single node. However, in the switch scenario, as you can see, if there are more nodes running the benchmark, because the server in that scenario is connected via 100 megabits, then the performance of the workgroup goes up and up and up until it finally consumes the entire 100 megabits available to the server. This shows the tremendous performance difference between repeated and switched workgroups. What does a PACE workgroup look like? Does it look any different? Well, a PACE workgroup, as you can see in this illustration, looks pretty much like a regular repeated workgroup. There's a hub in the middle that is star-wired out to the nodes. Star-wired in this case simply means that every system is wired directly back to the hub. There's a downlink. In this case, the downlink will probably be fast Ethernet or ATM, and it still goes down to a collapsed backbone device or hierarchy devices that concentrate the building that it's in. In a PACE workgroup, the difference between this and any other workgroup, until you start running multimedia applications, will be pretty much transparent. The general layout of applying switching in this manner will make networks look pretty much the same to end users and even MIS, regardless of whether or not they're repeated or switched. The big difference is that switched networks will have much greater capabilities. Another aspect of PACE is that it allows different kinds of data to be mixed together. In PACE, we call this implicit class of service. What is a class of service? Well, if you're a data application, you really don't care if your data gets through right now, just as long as it gets through reasonably quickly. But if you're trying to run a video conference, for example, then you want that video data to get through very rapidly. Going back to some of the application amalgams we talked about earlier, where you're mixing multimedia and other kinds of applications, assume that at the end system, the person wants to look at a spreadsheet. That user has to load that spreadsheet over the network at the same time while maintaining a video stream. That means that the end system is seeing two different kinds of traffic, the data traffic for the spreadsheet and the multimedia traffic for the video image. What PACE does is to create multiple logical entities out of a single physical entity so the traffic can be differentiated. For class of service, the important places to differentiate are all the mixing points in the network. What I mean by mixing point is where you're taking from both the old style traffic or classical data traffic and mixing it with the new multimedia traffic. Any system that does that sort of behavior or performs that sort of operation needs to take into account class of service. Now we'll see a tutorial animation that shows the difference between having class of service and not having class of service. In this scenario, we have a transmitter and a receiver. We're just going to show the transmit queue on the transmitter and the receive queue on the receiver as the data arrives. So you have a set of packets which are waiting to go. At some point, say a multimedia packet arrives. With regular Ethernet, this multimedia packet would be placed onto the end of the transmit queue. It would wait its turn to go out and eventually would go out. Then, as it arrived at the receive queue, it would go on the end of the receive queue, and eventually, as the receive queue was processed, it would be noticed and dealt with. Now again, using this very simple scenario, see what the difference would be with class of service. You have a queue of packets waiting to be transmitted. The multimedia packet arrives, and this time the multimedia packet goes onto the front of the transmit queue, which means it goes on the wire much more rapidly. Then, after the packet is received at the other system, rather than going on the end of the receive queue, the packet would go onto the head of the receive queue, so it would be processed much more rapidly. This is a very simple scenario, and obviously in a real system there would be intermediate systems which would have to be managing queues also, and there would be some other considerations in managing these various queues, but the basic notion of class of service is clearly shown. So the other aspect that has to be dealt with is jitter. PACE uses something called interactive access to deal with jitter. The observation made in designing PACE was that Ethernet was originally designed to service a large number of nodes contending to get access to the medium. In a workgroup switched network, there are only 2 nodes per Ethernet segment. By understanding how the end system works, how access is granted onto Ethernet, it's possible to construct a workgroup switch in such a fashion as to greatly reduce the jitter associated with an Ethernet network. To explain this to some degree, we'll have to discuss back-off on Ethernet. What is back-off? On an Ethernet network, there is no attempt to stop nodes who happen to start transmission at the same time. When this occurs, something called a collision happens in the network. Everyone who participates in the collision can determine that this collision has occurred. What they do at that point in time is to start into what's called binary exponential back-off. A lot of technical terms, but what it essentially means is that when they need to back off, they choose a random number. If they continue to find contention, then they choose another random number. Every time they choose a subsequent random number, they increase the range over which they choose a random number by 2 and try again. Here is a simple animation to explain this. In this case, we show just 2 nodes. Both nodes attempt to transmit on the network at the same time and collide. So they both go into their back-off. The first time they attempt to back off, they both can choose from a range of random numbers over the range of 0 to 1. It is reasonably probable that both might choose the same random number. So assume they both choose 1. Then they would collide again. They both would go back into back-off again, and since they were unsuccessful in transmitting the first time, they would double the range of numbers from which they choose. Now it could be from 0 to 3. So assume in this case they choose different random numbers. The node that chooses the lower number is going to win the collision, and that node is going to get to transmit. The other node, however, will lose the collision. Assuming there's another packet to be transmitted, they would collide again. What would happen this time is that the system that won the collision will have its range of just 0 and 1, whereas the system that lost the previous collision will have a range of 0 through 7. This makes it much more likely that the system that lost the last collision will lose the next collision. It's the lower numbered choice that wins the collision. So if all this happens again, where one continues to lose and the other one continues to win, the winner will have 0 and 1, and the loser will have 0 through 15. And this continues on in this fashion until eventually the one who's losing the collision gives up and starts all over again. In Ethernet, this is defined as being able to occur 16 times, so the amount of wait time can become very long. So let's look at another animation. This animation will show the effects of this back-off behavior in transmitting a set of packets. Then we'll look at how interactive access changes this behavior. In this case, we still have our transmitter and our receiver, but now we have a transmit queue and a receive queue, and these two systems are going to be transmitting packets to each other. With regular Ethernet, they both attempt to transmit. They have a collision, and there may be multiple collisions, but eventually one of the sides will win and they'll transmit the packet. As soon as this occurs, it's very probable that the next time the other side will lose the collision. So what will happen with the next packet is there can be a collision, but the one who won the last time will probably be the one who wins again. So another packet will flow from that system. And then maybe there'll be another collision, but because there are more packets in the transmit queue, then probably again that same system will get to send its packets. Now eventually, either because the other side resets and starts all over again, or it just happens that the other side wins, the other system may transmit a packet. Then if it has several packets to send, it may get to send those packets for a while, so we can watch this happen. Now, in a scenario with interactive access enabled, we can watch what happens. Both systems have packets to send, so they try to send. There's a collision. Since you're using standard Ethernet, one system wins, one system loses. But what happens this time is that the switch is aware of how Ethernet works. It changes its behavior to make sure the network is shared fairly. So rather than one system getting to send several times in a row, what happens now is that the other system gets to send, and then the original system gets to send, and then the other system gets to send, and so on. The network is shared fairly. In addition to creating a fairness of shared bandwidth, this also creates reduced latency because one system doesn't get to send several packets in a row before the other system gets to send the packet. In this animation, let's combine both of these notions. Again, we have our transmitter and our receiver. They both have transmit and receive queues. This time, what we're going to show is that with regular Ethernet, they're having the effect of getting several packets through. They're also having the effect of when the multimedia packet shows up, it goes to the end of the queue. Because of this combination of effects, we can see that it takes a long time, many packet times, to get that multimedia packet from one system to the other system. Now looking at the scenario with both interactive access and class of service implemented, we see that as the packets go across the network is being shared fairly. Then when the multimedia packet arrives, it gets to go to the head of the queue, and because the medium is being shared fairly, it gets to transmit out on the medium very rapidly. When it arrives at the other queue, it immediately goes to the head of the queue so it can be processed very rapidly. Now we're going to do a live hardware demonstration. All the animation is very nice, but it's good to see things actually working over real hardware. What we're going to do is set up a live video feed across the network. We're going to load this network with data traffic so you can see the effects of running a network as a regular Ethernet as opposed to a PACE network. When you look at the screen, you can see some buttons across the top. Each of these buttons represents 1 megabit of network throughput as seen by this particular system. So what we can do is set the network to regular Ethernet and start transferring a video. As you can see, there are roughly 4 megabits of the video traffic occurring on the network. The video and sound are fine. In fact, this is probably the way you've normally seen multimedia over Ethernet demonstrated, with a network that really isn't at high loading or full loading. However, we're going to start up the data loading part of the application. And now the two systems will start transmitting large amounts of data in addition to the multimedia. So as you can see, the utilization of the network is now much higher, and the video and sound are breaking up substantially. Let's take this system and enable the PACE aspects of it. We'll turn off the data loading and enable PACE. Again, the video is roughly 4 megabits and it's fine. But now we're going to enable the data loading. So as you can see, both the audio and video are fine with PACE enabled. If you notice utilization buttons, you can see this utilization of the network is actually much higher than the other network. We have a graph comparing the two which shows that with PACE, there's very little lost bandwidth because the video information is arriving on time, and the rest of the bandwidth is being made available for data. There are very few collisions, and what collisions do occur are handled very efficiently. However, with the regular Ethernet case, a lot of video doesn't get delivered on time, so that bandwidth is lost. And there are also a lot of collision and dead time caused by these collisions. Also, we can look at the results of running this demonstration on the sniffer. When you run the data loading on the network and look at it with the sniffer on an Ethernet network, you can see exactly the effect we're discussing. You can see how one system gets to send several packets in a row, and then the other system gets to send several packets in a row. The number of packets they actually get to send is somewhat random and depends on the characteristics of the protocol and the randomness of the backoff algorithm that we discussed earlier. Now, if we look at the sniffer output when PACE was enabled, you can see that the packets are flowing back and forth with very close to minimum spacing, and the network is being perfectly shared between the two systems. Now that we've seen some technology demonstrated, let's talk about the future. Let's talk about how multimedia is going to happen on networks. Our focus here today has been really on a workgroup application, switches and PACE, which are focused primarily at solving workgroup problems. Fortunately, a significant aspect of solving the wider enterprise problem will be solved by the emerging deployment of ATM as a backbone in networks. ATM innately has the capabilities of providing low jitter and low latency through ATM networks, which are required by multimedia services. However, ATM is a fairly new technology and still fairly expensive, so it's not reasonable to expect that a customer will wait until ATM matures and then gets down to the same price point as Ethernet. Nor is it reasonable to expect that a customer will throw away billions of dollars worth of Ethernet equipment to put ATM on the desktop. So what will occur to a large degree will be a mixture of workgroup Ethernet because that's what's there and that's what's cost effective with ATM backbones. Also, inside buildings, a lot of LAN switching will be used. For example, on Ethernet, PACE is speed independent. You can provide these services at either 10 or 100 megabits per second. So using 100 megabit links to connect together Ethernet switches and then connect them to an ATM backbone may be very cost effective while still preserving the capability to deploy multimedia. In the general enterprise situation, multimedia needs to be carried over both LAN and over WAN. WAN deployment can be addressed to some degree by ATM, but realistically must be addressed in the shorter term. Fortunately, the way PACE is defined, it's possible to map the multimedia traffic onto connection-oriented services across WANs. So now, to summarize, we looked at why multimedia is part of a fundamental trend of computing, the productivity benefits of multimedia, and the usefulness of multimedia going forward cannot be questioned. What may be questioned is the exact deployment time frame. One of the inhibitors to its deployment is an infrastructure capable of supporting multimedia applications over networks. Some, in fact, say that multimedia doesn't need to be distributed over networks, that CD-ROMs and other mechanisms are quite sufficient. However, when you go back in time and look at networks at their beginning, there was something called sneakernet. What that literally meant was, when you need to share data, you wore your sneakers and you walked over to whomever's desk it was and copied the data on the floppies. I don't think it's realistic to expect going forward the CD-ROM version of sneakernet is going to be particularly useful. It is much more reasonable to create a centralized library so that everyone has access to the data and can look at the training, news information, lots of other applications via the network. This is much better than having to wait till this information has been put on CD-ROM and then moving the CD-ROM around the network via sneakernet. Further, we've seen at least one approach to reusing the existing infrastructure for multimedia applications. This reduces significantly the investment in dollars, equipment, and training which must be made to deploy multimedia. This means that the dollars can be targeted more at the actual applications themselves and less at totally replacing and upgrading the networking infrastructure. So finally, I hope you've enjoyed hearing about multimedia on Ethernet. For those of you interested in learning more about Ethernet, I have done another UVC video that specifically addresses Ethernet. I've certainly enjoyed putting this presentation together, and I'd like to thank the many people who've assisted me in doing so. Thank you for your kind attention.